Today's discussion is also the continuation of our previous discussion, that is on piezoelectric ceramics. We will also continue after this is complete on pyroelectric materials as well. Earlier we have introduced the concept of piezoelectricity, different coefficients and their directional properties as well as the tensor characteristics of the coefficients. We started with the discussion of what we call the morphotropic phase boundary, particularly for the most important ceramic materials, that is known as PZT or lead zirconate titanate. We are looking at the phase diagram of two components, two perovskite compounds, that is lead zirconate and lead titanate. Both of them have the perovskite structure. So, they go into complete solid solubility, and you have the ferroelectric to non-ferroelectric phase boundary at around 50 mole%. When you mix about 50-50, you have a ferroelectric to or both ferroelectric phases. Before that you have a rhombohedral phase, and with a higher lead titanate content it goes to the tetragonal phase. So, that is the morphotropic phase boundary which is around 50 mole%, and the Curie temperature increases. It is lower from the lead zirconate and it increases as we increase the percentage of lead titanate. Incidentally, the Curie temperature of lead titanate is around very close to 500 degrees, whereas that of lead zirconate is only around less than 250 degrees centigrade. So, this is the variation of the Curie temperature, and this is the polymorphic phase transformation, that is ferroelectric rhombohedral to ferroelectric tetragonal, and that is what we known as the designate as morphotropic phase boundary. Now, this has a very significance so far as the particular property or the piezoelectric property of this composite or this solid solution is concerned. That is given in the next diagram. Once again, it is plotted as a function of lead titanate percentage or mole percent lead titanate, and here what we plot is coupling coefficient. So, that is one of the very important property of piezoelectric materials. So, as we have discussed earlier, it is the ratio of the energy conversion, how much energy is given in or input energy to that of the output energy to the input energy. And one can see the coupling coefficient is not only a function of the composition, but it goes to a maximum very close to the or exactly at the morphotropic phase boundary. Okay. So, that is the reason the composition of the morphotropic phase boundary at different temperatures are also important. So, we get a peak of the coupling coefficient at the morphotropic phase boundary. That means, when we are talking about PZT, although it forms a complete solid solution between 0% to 100% composition, either lead titanate or lead zirconate, but a more useful composition is in the around 48-52. In fact, not exactly 50-50, but it is about 48-52. So, that is the importance, because the coupling coefficient increases at the boundary composition, not either rhombohedral or tetragonal phase. So, it is the boundary of that we get the maximum coupling coefficient. With this background, let us look at or compare some of the piezoelectric properties of certain important piezoelectric materials, particularly ceramic materials here. Quartz, although it does not have a perovskite structure, but quartz is a very good piezoelectric material, and its coefficient is about D33 in this case. It is around 2.3, whereas G33 voltage coefficient is about 50. So, this is the coulomb per Newton, and it is voltage per Newton. Okay. So, this is about 2.3, whereas that is 50. If you take barium titanate is also a ferroelectric as well as piezoelectric material, and its piezoelectric coefficient D33 is 190, whereas the voltage coefficient is only 12. Okay. So, it is in fact less than the voltage coefficient is much less, it is about 12 compared to quartz, whereas the strain coefficient and the D33 value is much more. PZT is one of the most important and widely used piezoelectric material, that is 268. It can vary with composition, with kind of impurities it contains, additional dopants you add. So, depending on that, although we are just talking about PZT here, but actually it has many variations, and the composition may vary from different percentages of lead zirconate and lead titanate, and also one can add different intentional impurities. So, it varies over a wide range about 268 to 480, which is much larger, any of the other piezoelectric materials we consider here. In fact, these are the most important piezoelectric materials normally used in different devices, but so far as the D33 value is concerned, is very high. Its G33 is also fairly large. Now, in addition, you have few other titanates or niabates. For example, lead niobate D33 is 80, lead titanate is another piezoelectric material, and it also has another important property, we will consider that. It is also a pyroelectric material, it is about 47, lithium niobate is 6, and lithium tantalate is still small. So, one has a very wide range of D33 values, piezoelectric coefficient, and among them PZT is of course a much greater advantage compared to others. Now, looking at PZT in particular, it has different other properties. Some average property has been shown in the earlier table, but here we have presented more detailed properties only of PZT. Incidentally, PZT can be different industrial standards. Industrial standards have been prepared for PZT material, and they have been designated by some numbers. Okay. For example, PZT 5H, it is called soft PZT or soft piezoelectric material, whereas PZT 4 another industrial standard material, and it is called hard piezoelectric material. Well, basically they differ in different compositions. There are different additions of impurities, maybe antimony, niobium oxide and so on are added, and also one controls the microstructure. So, by doing that, just like soft ferrite and hard ferrite means you have a large BH curve. Similarly, A soft ferrite has a very large area of the ferroelectric hysteresis curve, whereas this has a smaller ferroelectric hysteresis curve. So, hard ferrite hard PZT means it is difficult to pole, polling needs higher voltage, and once however once you have polarize it, it is difficult to depolarize it, whereas this needs relatively low voltage, and also the Curie temperatures are different. Okay. So, Curie temperature, for example, you can see here this is much higher, this is much higher Curie temperature 323, whereas this is 193. Okay. So, compared to this one can enhance the Curie temperature to fairly large values. So, there is one group of materials called soft piezoelectric material, soft PZT basically, and this is hard PZT, and they have some kind of designations as well. Permittivity varies from 3400 to 1300. Okay. In this case it is about 3400, it is only 1300. Dielectric loss it is little higher, whereas this is little lower. Curie temperature as mentioned, this is 193 around 200, whereas it is 320, more than 320. Piezoelectric coefficient, there are 3 different coefficients have been reported given here. One is D33, it is 593, and this is for this group of compounds it is 289. This is minus 274 and 123. So, this group of material or this particular standard is used for one certain application, and this has different applications. Okay. So, 15741 and 496. Coupling factor, that is the energy conversion ratio, is fairly high, one can say 0.75, 75%, and this is 70%. These are comparable. This is 38 and 33, whereas K15 is about 67 and 70. So, these are more or less comparable, but the most important thing is their coupling coefficients are quite different, and the Curie temperatures are quite different. Okay. So, in addition, of course, the permittivity, that is the dielectric constant. Dielectric constants are also quite different. So, you have 2 different standards, industrial standards, depending on their composition and depending on their microstructure. So, you have for different properties, you can vary the property to some extent. As you have seen, PZT is one of the very important piezoelectric ceramics used in industry. We will see large number of applications in a few moments, but before that we like to introduce another group of materials based on PZT or based on other piezoelectric material as well, that is called piezoelectric composites. Now, they have a very useful applications and useful properties. One has to consider here the ceramics is basically a brittle material, as we have discussed earlier as well, and in a piezoelectric effect we have both mechanical stress and electrical polarization. So, there is a correlation between that, and each ceramics, any ceramics which is used as a piezoelectric material has to be stressed, mechanically stressed. But ceramics although have a high piezoelectric coefficient, but they have a very poor mechanical property, particularly their elasticity is very low, and they are quite brittle materials. So, you cannot stress, one cannot stress them to a large extent, and therefore, you have a limited application. The mechanical property, because of the poor mechanical property, poor elasticity, you do not get to utilize the real piezoelectric effect in a whole range of stress. One way of avoiding it or improving the property is to make a composite with some polymer, and polymer may or may not have some piezoelectric property. Some of the polymers do have some feeble piezoelectric property, but most of the polymer do not have the piezoelectric property, but it provides you the most important mechanical advantage. So, there is a important range of compounds or important range of materials or composites which have been prepared out of piezoelectric PZT and polymer. Now, this is one example what we have just shown. This is one example of how these composites have been prepared or have been conceptualized. As we have discussed earlier, that piezoelectric property is a directional property. So, the alignment or the way the ceramics are aligned with respect to the matrix is quite important. Here one example has been given as if some of the rods, square cross section rods, have been embedded in a matrix of polymer. Okay. So, this is one example where all of them, all the ceramic materials are aligned in a particular direction, they are not randomly placed, they are intentionally been placed in a particular direction. Okay. So, this particular compound or this particular composite, the kind of connectivity it has, what they call the connectivity of these compounds or the composites, this is what one call the 1-3 connectivity. That means, the polymer is a continuous phase. Okay. Polymer is a continuous phase and ceramics has a connectivity only in one particular direction, either z direction, one can say it is in the z direction. So, it is a 1-3 connectivity. Polymer is connected in all the 3 different directions, whereas there are isolated one can say rods or fibers, whatever you can call them depending on the dimensions. One can say it is rods, or one can have these days with the advent or with the preparation of the nanofibers, one can also have nanofibers of ceramics, but they are all aligned in a particular direction. Similarly, you can have many different kind of composites, once again with ceramic polymer composites. For example, one can have 0-3 connectivity. 0-3 connectivity means ceramics is actually in the form of particles or isolated grains. They are not even like rods or fibers. So, rods and fibers are one dimensional, whereas if you have isolated particles, that will be 0 dimensional. So, from that concept, it is actually a polymer reinforced with particulates, PZT particulates or piezoelectric particulates can be called a 0-3 connectivity. One can also have various other connectivities, like it can be a 3-3 connectivity, it is quite difficult to make, but if you have a continuous porous structure of ceramic, one can make a continuous porous structure of ceramics and the pores are filled up with polymer, that can be a 3-3 composite. One can have also a 2-2 composite, 2-2 in the sense polymer is continuous in the 2 dimension and the ceramics as well in the continuous in the 2 directions. So, basically that will mean that we have a lamellar structure or a alternate layers of ceramics and polymers. Okay. So, that can be, so polymer is continuous in the xy direction, ceramics is also continuous in the xy direction, but in the z direction none of them are continuous. So, one can have a lamellar structure or a layered structure of ceramic and polymer. So, there are many different ways in this illustration. We have just given only one, that is 1-3 connectivity, but we can have many different connectivities, and depending on that one can have different properties. Okay. So, in which direction the stress is applied or will be applied in a particular device, and in which direction the voltage will be measured, or reverse way, which direction the voltage have to be applied and the stress is required. So, that way one can have different connectivities and different composite materials. So, ceramic polymer composites, in addition to pure ceramics, is also a very important group of piezoelectric materials, and they have tremendous amount of industrial applications. We will try to discuss few of them in a few minutes. So, this is all about ceramic polymer composites. Well, with this background, we come to some of the important piezoelectric devices, that means the application of the piezoelectric material. Well, some of them we have encountered in our daily life. For example, a gas lighter in your kitchen, one uses a gas lighter, and that is nothing but a piezoelectric or piezoelectric ceramics is suddenly a very high stress is generated, which generates a very high voltage, and then it is allowed to go to the ground. So, you have a spark. So, that is very simple, but quite important application of piezoelectric material. Normally PZTs are used. Then you have electronic buzzers. Well, if you want to make an electronic sound electronically by applying electric field, you like to vibrate a particular bimorphs, and the frequencies can be varied by changing the dimension, changing the composition, changing the design of the vibrators. So, one can really make different kind of frequencies, generate different kind of frequencies, different kind of pitch for the same sound, and that is how most of the buzzers we use these days in different forms, including the bell rings, or the doorbells, or computers, alarm clocks, so many of them, including your musical instruments. All the musical instruments today you have the so called synthesizers, and the sound is actually made with the help of piezoelectric buzzers of different frequencies and different tones, different pitch, and so on. So, one can generate electronically different sounds. The loudspeakers today, most of the loudspeakers, even the even the mouthpieces are all made of piezoelectric devices or piezoelectric. Either it absorbs sound wave and generates electricity, electronic signal which can be amplified, or the reverse way, one can give electronic signal and then generate sounds. So, all these public address system, most of them actually generates are based on piezoelectric buzzers or sensors. By the same principle, one can use huge variety, large variety of pressure sensors, load cells of different instruments, and wherever we need to either measure the total load or the total or the particular pressure, one can use this kind of a system. We are not going to the details of the designs and all these, but just using the basic principle of piezoelectric material or piezoelectric coefficient, one can design different kind of load cells from few grams to several tons. Okay. So, there are of course complicated designs, but at the heart of this sensors there is always a small piezoelectric material of right property. So, gas lighters, pressure sensors and electronic barges are some very common examples or common uses of piezoelectric material. In fact, one can say that among the electronic ceramics or electronic materials, piezoelectric materials are most widely used, and the total number of devices one can make out of this is enormous, various different types. Next we come to the ultrasonic transducers. Once again, this is another area where piezoelectric materials have been extensively used for different applications. We all know about ultrasonic cleaners, ultrasonic baths, for even for cleaning any particular system. You generate expose it to ultrasonic waves, and that actually loosen the darts and so on. So, ultrasonic cleaners and ultrasonic baths are extensively used for cleaning purposes, whether it is semiconductor industry or any chemical industry, everywhere. Many, even in laboratory conditions, we use ultrasonic baths. So, or sometimes even what we call the sonification. Okay. Sonification these days is a very important processing, chemical processing instrument or technique by which one can make different kind of products or different kind of, even ceramic powders can be used, can be made by sonification. So, all those ultrasonic sources uses piezoelectric systems or piezoelectric materials. So, by so that is another very important area of piezoelectric application. This is the basic structure of a ultrasonic transducer. Basically, you have a piezoelectric material which is sandwiched between two layers. One is what we call the backing plate, and there is called a matching layer. So, apply different pulses, okay. It is of different frequencies, and that responds, this responds and generates ultrasonic waves or sound waves. So, it is a mechanical, obviously mechanical wave. So, electrical signal is converted to a mechanical wave, and different frequencies can be made. It is not just by changing the pulse or pulse width or the frequency of the pulse, but by designing this particular structure, one can change the frequency. It can be varied from kilohertz to megahertz, and it is a very, very useful source for ultrasonic sounds or ultrasonic waves. And these are very thin, of course. It is not a very both thick and thin, depending on how much power you need. So, if you need small power, you can have a smaller device. If you need a very large power, then one can think of even ring type PZT ceramics. Okay. Very large size bulk PZT ceramics can also be used as transducers for different purposes. Okay. We will see some of the, we will mention there is one application in submarines where they call it sonars. They can be several 100 kgs of PZT material can be used for that purpose. So, ultrasonic wave generators can be very thin to very large sizes. Okay, coming back no, I will right. Now, these ultrasonic transducer are extensively used for two very important applications. One is medical diagnostics. Medical diagnostics is a important area where you use ultrasonic transducers. Another area, of course, as I mentioned, are underwater sonars, where one can detect enemy submarines. So even sometimes one can detect the different kind of other species like fish and other things by ultrasonic sounds. Okay. So, the basic thing is you generate ultrasonic, the basic principle is for detection, I would say. First of all, you generate a ultrasonic wave, and that will allow it to reflect back. So, ultrasonic waves moves forward, reflects at a particular surface or a obstacle, and then it comes back. So, it comes back. So, the same thing also acts as a source. Okay. So, it is not only ultrasonic generator, but it also acts as an ultrasonic source sensor. So, this source the source and detectors becomes the same with some phase lag. So, that is how because of the reverse property, the direct as well as converse property of the piezoelectric material, the same material or the same system can be used either as a source to generate ultrasonic sound, ultrasonic waves, and also detect ultrasonic waves in the reverse manner. So, this is basically the technique by which ultrasonic transducers is used. Of course, in cleaning systems you do not need any feedback, you do not need any kind of sensor, it just generates the wave or generate the ultrasonic beam. But in medical diagnostics or underwater sonar, we need both. You need a source, and then the reflected beam, the reflected wave must be detected, and its characteristics both in intensity and the phase lag has to be measured. Now, in medical diagnostics, as you know, we always use ultrasound techniques. So, all of them actually use basically a piezoelectric system. Now, in these two systems, we are actually trying to diagnose a fluid system, right. Underwater, it is the ultrasound is moving through a fluid medium, and when it is moving through a fluid medium, not to a solid medium. If it is solid medium, that is not a big issue, because the material or the the generator is also a kind of solid, right, and the interface, if it is a solid interface, the problem is less. If it is a solid liquid interface, then the transmission becomes difficult, because at the interface you have what we call a big impedance, okay, acoustic impedance. Acoustic impedance gets generated when the sound wave or the ultrasonic wave is generated within a solid medium and then moving to a liquid medium. So, there the impedance matching is very important, and some of the properties which are important. Right. Some of the properties which are listed here, you can see one of them is Z. One of them is Z is the acoustic impedance, just like electrical impedance, equivalent of resistance. So, here also you have an acoustic impedance, and that is very important. That is very important for proper transmission of the wave from the solid medium to the liquid medium. and you can see PZT ceramics, this is about 20 to 30, okay. That is the impedance, whereas there is one variety of there is one variety of polymer which is PVDF, the polyvinylidene fluoride. That is also a piezoelectric material, of course, with a very low coupling coefficient, relatively low coupling coefficient, and the epsilon prime is also quite low. Okay. So, the dielectric constant here is quite low, about 10, whereas the dielectric constant of ceramics is very, very high, and that makes that creates a little bit of problem so far as the Z value is concerned. Okay. So, that Z value, I think there is little mistake here, it should not be this value must be low. Okay. This value must be low, I have to check this value. I think it is not a right because the dielectric constant of PVDF is much smaller, but or for that matter for any polymer dielectric constant is relatively low, whereas PZT being a ceramic material and the dielectric constant is much higher. So, one needs a lower dielectric constant material, at the same time better coupling coefficient as well as the quality factor. The quality factor mechanical Q comes from the high coefficient, the piezoelectric coefficient. Okay. So, its piezoelectric coefficient is less, but its density also low and the dielectric constant is also low, whereas these three values for the PZT ceramics or any ceramics for that matter is very high. Density is high, the dielectric constant is very high, and consequently you have a very high Z value. So, normally to reduce the Z, I will check and find out, this is not the value. This is one we mix, we have talked about PZT polymer composite or ceramic polymer composite for the piezoelectric materials, and in such cases where you need a low impedance and low dielectric constant, you mix up with PZT with polymer. So, you make a polymer ceramic composite, and those are very important, for the medical diagnostics as well as some of the sonar applications. Okay. So, this is a very important compound which is used for the transducer applications. Okay. Compared to PVDF or PZT, we get a much better properties here, and that is where the polymer ceramic composite becomes quite handy so far as the transducer application is concerned. So, medical diagnostics we have discussed, and then underwater sonar. Underwater sonar, of course, again one needs a good impedance matching with water, and therefore, polymers ceramic composites are quite useful. Basically, one needs the purpose of the sonar is basically you generate, it is used primarily in submarines or the navy ships, where you want to detect under the water any enemy ship or enemy submarine and so on. So, you generate an ultrasonic wave, get it reflected from the emissives and then you detect it. So, by that process one can find out the detection of some obstacles in presence or in front of the Navy ships or Navy submarines. Okay. Another very important area which has not been listed here, but once again ultrasonic transducers are very important for that, that is for flaw detection. Okay. Flaw detection in metallic systems or in even any other material systems. Okay. It is the ultrasonic flaw detection system, and there also you generate some flaw and then generate some ultrasonic wave, ultrasonic signal, then let it transmit through the material, and after it is getting reflected from a crack or a grain boundary and so on, one can particularly if there is a pore or a flaw crack particularly. So, a crack gets deflected and you get the detection. So, that is a very important technique of ultrasonic flaw detection system. So, that is all so far as the ultrasonic transducers are concerned. There may be many other applications, but these are more important applications. Then the other category is resonators and filters, once again a very important component of electronic systems. In many of the electronic systems one needs either resonators with some frequencies, and then also you need filters where one particular frequency has to be isolated from a band of frequencies, and there also these piezoelectric detections, piezoelectric filters are important, and the construction of such filters is like this. No, this is this we have discussed, sorry. Yeah. So, this is a resonators and filters. In fact, it is a thin wafer kind of piezoelectric system, and then you have two electrodes. One is the bottom electrode, which is fully circle or circular electrode, whereas the top electrode or one of the electrodes has been bifurcated into two pieces or isolated by an insulator. Okay. So, these are conducting layers, whereas one surface is full circle, whereas the other surface is actually a half circles, and by that because of the electronic or piezoelectric coupling, one gets a very bandwidth, a particular signal is allowed to pass through. Okay. The other signals or other frequencies are not allowed to pass through, and therefore, you have a what they call a trapped frequency filter. So, there are many different kind of filters, but these are piezoelectric filters is one also another application where you use this piezoelectric materials. Piezoelectric materials are also can be used as what they call ultrasonic transformers. Okay. Here again you have two pieces of material. In fact, as one knows that in a transformer actually you isolate two different electrical signals. They are not connected, but they are isolated, and one arm of the isolator has a one particular signal, another arm of the transformer has another signal. Here also one has this kind of an isolation. One is isolation, the other is of course the multiplication. The low voltage can be converted into high voltage, whereas of course one can see two different types of two pieces of piezoelectric material. They are polarized in two different directions. One is along the z axis and another is along the x or y axis. So, by that process one also can get a ultrasonic transformer. But another very important area of application of ultrasonic or piezoelectric material is piezoelectric rotors or piezoelectric motors. Okay. So, it is not only transformer, one can have a piezoelectric motor in which actually something can be allowed or made to move or rotate. Okay. So, that is unfortunately, I do not have the particular schematic picture of that, but one can make very thin or very tiny motors just like a rotor and stator in an electromagnetic system. Here of course, is not an electromagnetic system, it is actually a piezoelectric system, and piezoelectric system can be made and can be designed to make very tiny motors. These tiny motors are in fact one of the tiniest size possible. I understand it is about 2 to 3 millimeter in diameter and about a centimeter in length. So, as small as that motors can be manufactured and can be designed with the help of piezoelectric material, and then they are actually used in many of the electronic cameras, particularly the autofocus cameras, where the lens is allowed to move through the help of a piezoelectric motors. Other important device or one important use of piezoelectric system or piezoelectric material is what I call SAW device. Okay. It is SAW sensors, sometimes SAW sensors are also used for many gas detection or moisture detection and so on, but in addition more importantly they are used in many different kind of electronic systems. Okay. SAW device basically surface acoustic waves. So, by a what I call interdigitized electrodes, a finger kind of electrodes on the surface of a substrate. The piezoelectric surface is this one. It can be used either PZT is not normally used, it is mostly zinc oxide or lithium tantalate, lithium niobate. That kind of substrates are mostly used for making a SAW device, surface acoustic waves. So, the acoustic waves are generated not through the bulk of the material, but it is on the surface, and that there are normally a pair of such things, such interdigitized electrodes. The surface waves comes there, generates there, and then gets detected here. Okay. So, one can generate the surface acoustic waves on this and then get detected here. And in presence of different environment, as I just mentioned, if there is a moisture or some gas, this acoustic waves gets changed, or their characteristics as well as the velocity as well as the phase difference gets changed, and therefore, one can detect the presence of such species, the environmental species like that. So, it needs a piezoelectric coupling to generate this kind of surface acoustic waves. This we have mentioned earlier also, that actuators, in fact, piezoelectric materials are used both as sensors and actuators, because it has direct effect as well as converse effect. So, for pressure sensors we have that is basically a sensor, whereas an actuator is also makes a movement, mechanical movement by application of an electric field. So, one can use a single layer actuator just like a single layer capacitor or a disc capacitor. Here also one can use a disc actuator, a single layer actuator or a multi-layer actuator, and the basic principle is very similar to that multi-layer capacitor. Okay. So, there are very thin layers of PZD piezoelectric material, and then we have metal electrodes in the form of thin films, basically thick films. Right. They are, so depending on the number of the layers, the actual actuating or the load bearing capacity of this will be very very high, or can be increased or decreased. So, this is another area where piezoelectric materials can be extensively used, actually, multilayer actuators. We have seen earlier multilayer Moonie, the single layer Moonie, and this is also multilayer Moonie. So, just by we have a metal plate here, and that is to enhance the actuating property of the multilayer actuators. Well, that was more or less. One thing I forgot to mention, so far as the ceramic or the piezoelectric motors are concerned, not only they are miniature in size, but their torque is very high compared to the electromagnetic motors. The torque is very high at a much lower voltage, okay, and it does not of course make any sound, as it is very tiny, and there is no electromagnetic effect. It is only very tiny voltage is required to move, and therefore, one can have a almost noiseless movement, and the torque, overall torque compared to a size much larger. Anyway, that was more or less our discussion on piezoelectric material. The last topic in this series is pyroelectricity, the ability of a material to spontaneously polarize and produce a voltage due to changes in temperature. Okay. We have seen earlier, as you apply a electric field, the material gets polarized in a dielectric material. In a piezoelectric material, as you apply a mechanical stress, the material gets electrically polarized. Here is another phenomena where you change the temperature, not the electric field, not the mechanical stress, but just the change the temperature, and that will spontaneously polarize or electrically polarize the material, and that kind of material is pyroelectric. They are basically insulating material or dielectric material, and there is a relationship between ferroelectricity, piezoelectricity and pyroelectricity. So, all piezoelectric and ferroelectric material are actually pyroelectric, but their pyroelectric coefficients may not be very large. In principle, they have a pyroelectric property, but the coefficients may not be very large, and therefore, all the materials are not used as a pyroelectric material. This is the pyroelectric relationship. The pyroelectric coefficient P equal to dP dt. D is the polarization, electric polarization as a function of temperature, and that is the summation of different terms, that is the permittivity of the free space. Okay. The important materials, we will not be going to the very details of this, just to summarize this effect. Important materials are lead titanate is one of them, lithium tantalate, gallium nitride, PZT is also has some pyroelectric property, although may not be used to that extent. BST is basically a barium strontium titanate, and PM and PT. PM and PT we have discussed in terms of the ferroelectricity, and this is lead magnesium niobate and a solid solution of lead magnesium niobate with lead titanate, that also has a good pyroelectric property. Okay. Important applications are primarily because it is a temperature effect. So, one can detect the infrared. If there is a infrared radiation, one can certainly detect, because it will generate some voltage. it generates some voltage and that can be processed. In fact, in infrared cameras, one can really design infrared cameras based on pyroelectric materials or pyroelectric sensors. So, that is a very important area. It is in fact a strategic area. Infrared detection is one of the very important strategic techniques are used in strategic areas for detection of different items or different even different systems. Okay. And millimeter wave of course is of the same area. So, IR and then still further high up is the millimeter wave. So, pyroelectric materials have been used. There are many other sensors of course to detect IR, but pyroelectric material is one of the techniques by which one can measure IRs, infrared. Different materials like this, this is the coefficient, pyroelectric coefficient of different materials. Barium titanate, you can see 3Z PZT is quite high, lead titanate is also fairly high, PVDF, one of the piezoelectric polymers, has also some pyroelectric effect. Even cement paste have certain amount of pyroelectric coefficient. So, there are many BST and PMN, PT also have some pyroelectric importance from the point of view of pyroelectric property. Unfortunately, these coefficients are not with me at this point of time, but the materials are important. Okay. Finally, the last slide in this I think is the electrostriction. Maybe we are aware of the so called magnetostriction. Whenever there is a magnetic field, there is a volume change or dimensional change on the material. And similarly, there is a effect called electrostrictive or electrostriction effect. When a material undergoes polarization due to an applied electric field, there is a displacement of its ions and electron clouds are displaced, giving rise to minor changes in its dimension. So, there is a lattice change and therefore, any polarization ultimately leads to a dimensional change. This phenomena is called electrostriction. Okay. And this electrostrictive property or the electrostriction property is quite predominant in the relaxer ferroelectrics like lead, magnesium, niobate kind of materials. And in fact, although it is little different from piezoelectricity, but this property can be also made use of in some cases. So, this is different from piezoelectricity, but it is also not a reversible process. Whenever there is a polarization, there will be dimensional change in the positive sense, not normally in the negative sense, right. So, electrostrictive is another area. In fact, the humming noise you get from the transformers is primarily for the electrostrictive or sorry not electrostrictive, it is magnetostrictive property. Okay. So, because of the magnetization you get a dimensional change. Here because of the polarization, electric polarization, you also get a dimensional change, and that is what we know about electrostrictive property. That completes more or less our discussion on the dielectric properties, that is the insulators. We have earlier discussed ferroelectricity, piezoelectricity as well as pyroelectricity and their characteristics, their properties as well as some of the important applications in brief. Of course, I did not have much time to go into the details of the piezoelectric devices and the design and the kind of basic working principle of them, but I have just given you some idea about how those piezoelectric materials can be used for different purposes. Thank you so much for your attention.